Yeah, you're in.
All right, so we're here going deep with Adrian Marinescu,
Yeah.
and he owns the Object Manager. And we've already talked about on Going Deep, we've talked about the Cache Manager, the I/O Manager, and a basic overview. So can you tell us a little bit about the Object Manager? What is this? What is the Object Manager?
So the Object Manager is a system component which provides a uniform mechanism of managing resources, system resources. So there are few tasks the Object Manager achieves, and one is like have a common naming conventions across the objects in the system.
Okay.
Provides a way of accounting of objects, which contains like object retention, which is about how long an object is going to exist, and whether someone uses or not, and then it's about how much memory uses and how you charge a particular process for the memory used by a process, by an object. So the object manager basically manages its objects, and the object is like a piece of memory, like a data structure.
Okay.
Which contains a header and a body that is specific to a particular object type. So the field in the header are something that are managed by the Object Manager. Everything in the other stuff, the other side is managed by let's say the I/O Manager if it's a file object, and memory manager if it's a section object, and so on. So this is specific to a particular object type.
The body is?
The body.
Okay, and the header you control.
And the header is controlled by the Object Manager.
And what is that?
So here is some of the common functionality for the objects in the system, in the object header. And for instance, the header contains the number of references to the object.
Okay.
So every time a particular component uses the object, increases the reference count, and the Object Manager knows to keep the object and don't delete until the reference drops.
Okay.
So this is part of the retention mechanism. It also has a number of handles, existing handle open, and I'll talk about later about the handle tables and how processes access the objects from the user mode.
Okay.
It essentially keeps track of all those the handles that are open to this object, and generally the handle count is equal or less than the reference count. So every user reference is also accounted for the kernel mode reference.
Okay.
And we also have an object, a pointer to the object type, which contains the common functionality of particular object as opposed to a particular object type. For instance, if this is like a file object, this points to a file object type. And it contains a bunch of the methods and properties for that particular object type. And it also has the entire security model, Windows security model. It's built around this Object Manager, and the object header may contain also a security descriptor, which controls the protection of the object. And there is also a uniform mechanism how the protection is done. It also has, in several cases, a name information, which is the object name, and also the directory object, which is the parent of the object. And I'll go a little bit in detail on this naming. Okay. It may have information regarding the handle database. which is a mechanism where an object can keep track of all the processes that have handle open to the object. So, and I'll go actually deep in detail when we talk about the handle tables. It may also have like some type information, which is a way to enumerate all of the objects of a particular object type. Let's say you want to enumerate all the objects for the file object. This optional information can be present in the object header, and we can find out all objects of
So now whenever we create an object in user mode, like for me, a developer way up there, it's being, you're the one doing the work for me as far as the reference counting and...
Right.
Okay.
Right.
So I just wanted to point that out.
Right.
Okay.
So now, the object manager doesn't have any knowledge about this body.
Okay.
It keeps only track of the size of the memory allocated for this body, and the content is basically up to the particular object type to be handled.
Okay.
So I talked a little bit about this object type, and this is that this contains the properties of all these objects of the same type, and I want to go up here a bit, talking about what the object type really contains. So there are several methods, which are essentially some callouts that the object manager provides for every object type, which are, for example, the methods are like open. Like whenever we open a handle to an object, we make this callout, and every object type can define a particular method to be called at that point. And open means when you create a new object, when you duplicate the object, and also when you open an existing one,
Okay.
like by name. And also we have like a close method, which is called every time an object is a handle is being closed. So you have like several handles to the same object. This is called like so many times. We have parse procedure, which is a mechanism to plug in a secondary namespace, and I'll talk a little bit about later when I talk about the name of the object manager.
Okay.
We have a security procedure, which is a mechanism that a particular object type can override the default security and can have additional control over the security of the object, and can perform additional tasks beside the existing object. And also could be like a query function, which is called whenever an application, a driver or user mode application wants to query the name of the object.
Okay.
This can also be defined by a particular type to be something else than the default procedure. And these are basically the main routines.
So basically, you're the resource manager for Windows. Is that one way? I mean, does anything not use the object manager?
We set some internal structures which are not objects,
Okay.
which don't count as objects.
Okay.
And the reason for that is because the lifetime for this is probably very short, and we don't have to incur all this overhead to have those the methods and have the object retention mechanism. So I think it's. I don't have like a number exactly how many are objects, how many part of the object, and how many are not objects.
Sure.
But it's not the entire thing. So object is just part of the kernel structures that provides the resource management. Okay, so I'll talk a little bit about how the objects are accessed from user mode and kernel mode.
Sure.
So this is like. So there are some differences here.
Okay.
And okay, so for instance, if we have this is like the user mode space, the kernel mode space. Although the address actually goes down like that, this is the higher address, and this is like the lowest. I prefer to put this way. So the object is essentially like a piece of, like a data structure inside the kernel space.
Mm-hmm.
And the process can, like process 1, can access this object through a handle, which is like which is a numeric value, which gets translated in a handle table, which is per process. Right, so this is also specific to this process inside the kernel mode, to a pointer to this object.
Okay.
And we can have like two different processes accessing the same object. They may have, they can have every kind of any handle for that information. This is like 1A, and this can be 1C, and it's perfectly fine.
Okay.
So they don't have to be the same. But the translation gets also to the same object, right? So two processes can share the same object through this handle.
Okay.
And assuming that the object is not named, is not currently in use temporarily by some other kernel component, we should see for this object as having like two pointer counts, two reference counts,
Okay.
and two handle counts, because you have to enter hop on 3.
Okay.
Right?
Now, can I ask a question now? How do you prevent this guy from changing the object to such an extent that it would affect this guy? Is that?
So,
you see what I'm saying?
So
So
actually,
you're doing a lot of locks, and
So actually, it's a bit more. So the access check is done when you open the object.
okay.
So if this process doesn't want to allow the other process to open the object, it has to properly set a security on the object, and the open will fail. We'll never get a handle to this object.
Okay.
The usual way to share the object is to use like names object, and they are open from the global namespace.
Ah.
So the handle table looks something like they are multi-level handles because so we don't want to reserve like a lot of memory for these handles, and we dynamically increase the handle table like on 3 levels. So the simplest, when you have like a process with very small number of handles, this is the handles are in the first level of the handle table. There is like an array of structures which contain the pointer to the object and the access mask, which tells what kind of access this object has for this object.
Okay.
When the entire number of handles for the first level are used, the object manager creates an extra level of indirection, which points to another level of entry. So it's like an array of pointers to the handle entries, and so on as the third level, which limits the total number of handles to a process like 2 out of 24, for instance.
Okay.
So the handle entry, the one that exists in the handle table, contains a pointer, as I said before. But for some memory optimization, actually, we keep some other states related to the object. For instance, we have a bit which says if the object is locked or unlocked. So temporarily we lock an entry to access the object, and we want to have consistency across multi-thread access.
Mm-hmm.
We can have also auditing mask, which is whether the object has to generate a security audit when it's used, or open or closed. And we have also an access mask, which contains generic bits and specific bits. The way the translation comes from the generic to specifics is given by an object type structure called generic mapping. Like what specific bits for a file, for instance, means are affected by a read, a generic read. So when someone changes the protection to be generic read, what means for a file to have a generic read? This is a translation to specific, for generic write to specifics.
So what does a generic read mean for a file?
Generic read means like reading the data inside the structure, means reading attributes, and actually there are some other fields inside that can be provided if you have the generic read access.
Okay. So basically what you're saying is there are modes of granularity for read types on an object.
Right.
Okay.
And the object manager doesn't have this information about the object type, the specific object type, and doesn't have to.
Okay.
Yeah, it's just a generic.
Because that's an implementation detail that you're not concerned about.
Right.
Understood.
Okay. So another interesting part of the object manager is the object manager namespace. This is okay. So there are inside the object header. There is a pointer to a directory object, and also a pointer to actual name of the object, a buffer. And the object manager namespace starts from root, which is like the backslash, and from this you can have directories and objects, which are in the same root. You can think of this like the file system. Okay. It's about the same model. You have directories and you have like files inside the directories. The same way you have like directories in the object namespace, which are different than the directories in the file system. Just a particular kind of object, and the files are replaced with any object, named object.
Okay.
Every object, so it has like, let's say directory 1 is like directory 2, and we have like an object. The object has a pointer back to the directory, and the directory has keeps track of all these objects inside the directory. Every time an object is inserted in a directory, the directory reference count is increased, so that it doesn't go away unless every single directory inside the object goes away.
Okay.
Go away. Also, because there is a reference to this object, the reference for this object is also increased for that. So named object, which has one handle count, is going to have two references and one handle count in the header. One for the handle, one for the name, and then one handle count.
Okay.
Temporary, though, the reference can go up and down, actually up for some temporary if they're accessible by some other threads, which I'm going to cover a bit about when I talk about the object retention.
Okay.
So an object can exist in the global namespace as long as it has one handle count at least open to the object, or is a special case with a permanent object. So leaving aside the permanent object, when you close the last handle to the object, this is automatically removed from the address space.
Okay. So now, for example, a file. This is the typical file on the file system is going to have, it gets designated this specific kind of name because it's an object, right? So is a file an object?
Yes, it's an object, but this is like a different. The file system is a different story.
Okay.
So this yeah, this actually comes to the second problem of supporting secondary namespaces. So somewhere in the root you have a directory called device, and somewhere here you can find like a particular device, like a hard drive.
Okay.
And that is actually a plugin for a secondary namespace, and all the file system actually are handled inside this namespace, and I can say it's just an extension of the object manager. So the directory of a file is not really a directory object. So we just see this device which has a parse routine, and everything is handled by the IO manager from that point,
I see.
which further goes to the file system drive, file system driver, and so on.
I see.
So the file system you don't see it here, but you can see here like events and semaphores and like other communication ports, IO completion ports, sections, a lot of other objects. Files are a little bit different.
Sure.
And the same are the registry keys. Registry keys also have an extension of the namespace, and the name parsing and security is also handled inside the registry.
So the the registry.
The registry.
Absolutely. Interesting.
So
Cool. So what you basically own the object manager,
right.
right? You own the code base for it.
Yes.
And how long have you been working on it?
It's like 6 years.
6 years?
Yeah.
Wow.
6.5.
And has it evolved relatively significantly since NT4 or NT 3.5?
So at the fundamental level now, there are a lot of improvement with respect to scalability and performance.
Yeah, I see you,
and,
you won an award for performance work. Nice job.
Yeah, thanks. And there are also like a lot of work with respect to reliability and those kind of work happens.
So, how, for example, how does the file system or the I/O manager or cache manager work with you? You guys, they rely on you, as we were talking earlier, to
Right.
manage their object references and lifetimes. Correct?
Right. So actually we expose a very, I think we expose the infrastructure, how to reference the objects and how to maintain the reference to the object. So for instance, we have like the kernel interfaces and have like the user interfaces. The kernel interfaces are provided for drivers, drivers writers, and there are APIs like reference the object and reference the object, and they have to make sure they match references to the references, otherwise they have leaks. And for the user mode is the handle interface. There are the handle interfaces.
Add ref release kind of things, or
those kind of accounting.
Yeah.
Okay. So
different story.
yeah, this is like a different story. It's more like a lower level.
Got it.
Actually, interesting about the handles is that beside the handles that I mentioned before, there are some pseudo handles, which is like the current process, which is like magic value. That we convert to when I go to the kernel, we convert to the actual current process structure. But there is no actual handle in the handle table for that. The same is like current thread. It's like some magic value for that. And there are also some values for the console object, which also have like a different special rule. But most of the time, the handles and interfaces provided for the Win32 layer are translated to the actual handles of the kernel objects. At some point.
Understood. And for the the kernel methods are available only to kernel components.
Right, only for kernel components. Some of them are only for internal kernel components, and some for drivers.
So the private APIs and the public APIs.
Some private.
And then in user mode, you're relying on Win32 and something else.
Right.
Okay. That's just a proxy to you.
Yeah.
Okay. Cool. So let's talk about how many processes and objects are you as your computer dealing with right now? There must be millions or thousands, let's say. So it has to manage, like, how big can one of these tables
So
get?
I think it's around like about a number of tens of thousands of objects on a system which probably just boots. If you talk about server scenarios, then the number is much higher.
Sure.
And yeah, obviously you have to deal with scalability, you have the multiprocessor machines and how you and synchronization issues.
Sure. So and then the multi-core, you have to deal with that world now.
Yeah.
Concurrency, but you're already writing concurrent code.
Oh yeah.
And you're an expert in it.
Yeah. No, the main question is how you make it to run concurrently without having like cache misses and how we avoid the cache collisions between different threads who try to access the same data, and those kind of.
That's a hard problems, huh?
Yeah.
And hard to track down.
It's I can say it's very hard to track down. It's, but you know, it's a problem that we have to deal with and to solve and make sure it's well.
Absolutely. Very good. So, all right. Now, what else were you going to talk about?
Okay, Steve.
So let's, how about take us through a path of something, an event happens in user mode, and you do something. Can you take us through sort of a path of like a typical action on the system where you're...
so let's say you have like a set event called, and this call receives a handle to the event that is going to be set. So this is the user mode, right? This is a Win32 APIs, which is pretty much like a thin wrapper over going to the system service. So it's going to translate to some NT API, NT function, let's say NT set event, which is a system service. You have the trap in kernel mode, and the set event API is going to reference the object by handle. So this performs the lookup, the translation from handle to object pointer. Isn't an instruction is. It does all this validation, respect the access, if the access is allowed to be set, if the handle is valid, and so on. And you can return failures, like if some parameter is not okay. So once you get the pointer, it goes to so once you achieve the pointer, then it goes and performs the actor action, which is like some internal API which set the event. Like the kernel function set a particular state for this event object, and because this all the way this function keeps a reference to the object, it has to dereference the object. So because you have the reference here to keep it to prevent going away while using it, we have to return the reference back, and then goes back to the user mode.
Now, does the user mode have to call the dereference object?
No.
So in other words, I can't be a user mode programmer and forget to dereference the object.
No.
Okay.
So all the system services, every single piece of kernel has to make sure that it matches the references, and should not expose the particular referencing problem to user mode application. So you cannot make design an API which would be something like set event here and no deref, and you have and you expect the user mode to call the deref later.
Sure.
Because then a malicious user can actually crash the system by calling this repetitively, like 48 times, and wrap up the reference count. And
understood. So you lock that down.
Yes.
Which is of course good.
Yeah.
Now, so a process isn't an object, huh?
Process is an object.
The process is an object.
Yeah, it's an object.
It's amazing how object-oriented the kernel is. So I always thought like object-oriented was sort of high-level thinking, whereas it's just I guess it's just a misinterpretation of what's going on. So the kernel is highly object-oriented.
Yes, it's very simple. Right? It's a very simple structure. I would say it's just maybe two levels. So you have like this generic object management, which is like a generic object, and then you have the first level, which are like the events and processes, threads, tokens, all this sort of section object and so on. And in some cases, you can have I think the file system, I would say this is like the second level, because you can have variation inside the file object. You can have like the pipe as a file object, you have like NTFS file of its own. So that would be like another level of.
And the benefits of being having this type of architecture, is it equivalent to, say, what a programmer would think about in terms of object-orientedness, encapsulation? We can stop there, but
Yeah,
you know what I mean?
Right.
There's slight parallels. So does it make the system more robust? Does it make it more flexible?
I think it makes more flexible.
Uh-huh.
It also makes robust, provides a uniform way to manage common functionality. So, for instance, we have NT-close object, and that function it's a generic function that applies to every kind of object. And we can implement it in one single way. And if there is like a particular, like a specific functionality that needs to be provided by an object type, then they have the way to plug in and to build some additional functionality on top of that. And same is like duplicate object. You can duplicate an object without really specifying, without being object specific. So any kind of object can be duplicated. Well, there are some limits there, but just give an idea. Same is to change the security and create a security, create a name. These are like generic operations that are vital objects. And same are in kernel mode. There are on top of this which have the pointer, the object pointer manipulation. There are also like common operations to reference, open by name, so on.
Very interesting. So what would the object manager look like in a managed kernel? You'd probably be heavily involved with exposing, with taking care of all the the internal stuff and everything outside of you. Just deal with like apparently type safe objects. Just a crazy question. I mean, but it would be interesting. So when you're writing code, you're writing C in assembly. Like, what do you do most of the day? C. Straight C.
Yeah.
Interesting. Very interesting. So it's highly performant. And,
Right. Yeah.
yeah. And is it a big project? The object manager?
Not quite.
Not quite.
No.
Just want to keep the kernel sort of fit.
Yeah.
Fantastic. So, do you have any questions? Oh, oops. So this is great. This is a good introduction to the object manager, which is really actually one of the most poorly understood, and not at least known yet. Most, I would argue, but I don't know. It seems to be widely used components, right? You're being used by memory manager, etc. You work on them on their behalf, etc. Do you rely on them for stuff as well? Or do you just, is there one way?
Well, we extend based on some other requests, if you want to improve the model and provide some additional functionality, but we don't take dependency of other components. I mean, it's like a file system or something, because it's supposed to be like structured this way.
Absolutely, because you're just a shared important kernel module that everything's relying on. So you can't rely on anything else.
Yeah.
Well, to some degree.
Yeah, to some degree, right.
Yeah. Well, you have to rely on the header information being.
Yeah, like the memory manager and so on, like
yeah.
allocations. Yeah, but we don't rely on a particular type of object that is going to provide something.
Cool. Very interesting. Well, is this unique for NT to be an object-oriented kernel? I mean, is that a fair question? I mean, is it one of the what makes us unique?
So I think it's so compared to Unix as a system, I think this is like one of the biggest differences.
Sure.
But I think saying that NT is like an object-oriented, I think is kind of too strong statement.
Too strong, sure. Okay.
Yeah.
And that's because of the way, because you have file systems.
Yeah.
Right.
So
I understand.
Yeah.
But
and I said there are a lot of structure, kernel structure, which are not like objects, and it's not like a common paradigm to have every single piece of code written in kernel to be this way. But it has a lot to do with sharing the data structures between drivers and users and the kernel and drivers and so on.
Cool.
And you have we need like a uniform mechanism to have this management for security, namespace, and so on.
Fantastic. And the registry, right?
Yeah, that would be like another plan.
So when you're in the registry, you're looking at classes. Are those like are those examples of are objects? Are they examples
So
of the
no,
namespace?
these are like registry objects. So I
Okay.
don't there's registry data structures. So the object manager doesn't have knowledge about this.
Okay.
So once it reached like the root of the registry, then this is handed over to the registry system, the configuration system,
Okay.
which continue to pass the name base and that. So essentially you have like something would be like if you have a name like A, B, C, D, right?
Mm-hmm.
For the object, once you open it and say B is like a plugin for a secondary namespace, the remaining namespace is handed over to that particular space. So we reach this object here, and when we find that it has a parse procedure, then we give the remaining namespace to the actual parse procedure, and they decide whatever to do with this namespace.
Okay. Interesting. So now, have you always been in operating systems as a developer?
Yeah,
Pretty much.
yeah, pretty much.
And Windows only?
Windows only, yeah.
Windows only. Wow. And you've been in Microsoft for
6.5
6
years.
and a half. So you came to work on
Right.
the object manager.
Yeah. Well, it's not only that. So I also work on the IPC mechanism kernel, which is called LPC, and also the Heap Manager, the user mode memory manager.
User mode memory. Now.
Yeah.
Okay.
So this was not like the only.
So yeah, because we're going to be talking to Landy Wang,
Mm-hmm.
and he's the kernel
He's the
mode
kernel,
memory manager,
yes.
and you on the user mode.
Yeah.
So can we talk a little bit about that? Like what?
Sure.
What is it? So what user mode memory manager?
So I think it's very well known outside as a Heap Manager,
As the heap manager. Okay.
and provides the functionality like to keep it simple. It's just malloc and free. Right. So allocating pieces of blocks of memory and free them.
Okay.
And there are some other functions on top of that, but basically this is what this is about. So how you manage the.
So when I call those, you do the work.
Yes. So it's not actually malloc. Malloc is like is the function exposed by CRT, the C runtime. The Windows APIs and Win32 are heap alloc, heap free, and to create a heap, like heap create.
Okay. And those are just proxies to you.
Yes.
Okay.
At some point there are like.
So what exactly happens when I call heap free? Like how are you freeing memory? Like what does that mean? So you're destroying the structures that you have in memory. You're destroying. So
yeah.
It's a good thing to think about.
Right. So okay. So there are some. I step back a little bit. So there are like operating like some OS level of APIs to allocate memory, virtual alloc, for instance.
Mm-hmm.
And allocating memory with this virtual alloc, it's aligning everything at 64K boundary. And it's very inefficient if you think at an application if just allocate, let's say, 8 bytes or something, right? So in order to have like very fine grain of memory blocks for this application, like very good locality and performance, then you have this user mode component which pre-allocates like a bunch of memory from operating system, and then does a management inside these large blocks for the application. And when you run out of space, and the heap is growable, can be extended, and go back and ask for more memory from operating system. And there are two ways to ask. So one is to use like reserve memory and committed memory. So we reserve for a heap like particular chunk, and if we need, so if we run out of this, we reserve even more. But inside every chunk, we have part of the memory committed or uncommitted. This is to save the commit charge for the process and the paging file and so on. So that
sure, that's interesting. Cool. Yeah, that's a lot. There's a lot going on down in the kernel world. And cool. So we've covered Cache Manager. Now, introduction to the object manager, and we're going to do the memory manager. What else should we check out? We got the cache, so we had the I/O manager and driver model with NAR.
So I think the LPC mechanism of the kernel, I think it's very interesting as well.
Okay.
So this was not exposed to the Win32, to the 32 layer, just internal mechanism.
That's fine.
But I think it's interesting.
So what is it? What does it do?
This shows the communication between two processes, or between kernel mode and user mode processes, and
so it's a communication protocol.
Yeah, it's a communication mechanism, which is very fast. It's supposed to be very. It provides like several method of data passing regarding with respect to the data size.
Very interesting. Great. Well, thank you for your time. I know you're very busy.
Thank you very much.
I appreciate it. It's great to talk to you. Thanks.